Long before the sweeping landscapes of the Mesozoic era were uncovered in fossilized bones across the world, the study of what we now call dinosaurs was in its infancy, a field only just beginning to take shape. Our journey begins in the early 19th century, during a moment of scientific awakening and keen curiosity, with a figure whose name may not be as familiar as some of the dinosaurs he studied, yet whose contributions were monumental: William Buckland. It was Buckland who unlocked one of the very first complete glimpses into the structure of a dinosaur through the discovery and description of Megalosaurus, a revelation that helped crystallize the reality of these ancient, mysterious creatures in the scientific consciousness. William Buckland was a British geologist and paleontologist born in 1784, and a man deeply fascinated by the ancient past. He was both a scientist and a clergyman, a combination that initially allowed him the freedom to pursue his geological interests with zeal. At a time when fossils were often misunderstood as curiosities or mythical remnants, Buckland took a distinctly rigorous approach. He believed that by studying fossils, one could unlock Earth's lost history. His early work focused largely on geological formations in England, where sedimentary rock layers preserved many prehistoric secrets. It was in the early 1820s that Buckland became associated with one of the most pivotal fossil finds to date. The story begins with the discovery of partial dinosaur bones in various locations around England, primarily in the limestone quarries of Oxfordshire. It was these fragments that first prompted Buckland's keen interest, pushing him to study and articulate something entirely new to science: a complete skeleton of a large prehistoric reptile. The dinosaur at the center of this story was Megalosaurus, a creature whose name means great lizard. Though parts of Megalosaurus fossils had been found earlier, it was Buckland who played a crucial role in describing and interpreting these remains in full detail. In 1824, Buckland published the scientific description of Megalosaurus based on the bones collected from the Stonesfield Quarry near Oxford. This publication was the first formal scientific description of any dinosaur, making Megalosaurus the first named dinosaur. Though the term dinosaur had not yet been coined, it would not be until 1842 when Sir Richard Owen introduced that term. Buckland's Megalosaurus revelation was monumental in several ways. For one, it was the earliest attempt to reconstruct a prehistoric reptile from enough bones to comprehend what the creature might have looked like, at least in a skeletal form. Although the skeleton was not complete by modern standards, the collection of femur, jaw fragments, vertebrae, and other bones were abundant enough to give a convincing depiction of a large, powerful, carnivorous reptile roaming ancient landscapes. His work was not merely scientific description. Buckland's interpretations helped shift the perception of fossils from mere oddities to real remnants of once living beings. This laid foundational groundwork for comparing extinct animals to living ones, articulating the concept that these strange creatures had actually existed long ago and were part of the natural history of Earth. This was a revolutionary perspective in early 19th century scientific thought and heavily influenced subsequent studies on prehistoric life. One particularly fascinating aspect of Buckland's work was his attempt to fit Megalosaurus into the then-current biological framework. He was careful to treat it not as a mythical monster, but as an ancient reptile, albeit one unlike any living today. This helped spark an entirely new scientific curiosity: the pursuit of understanding species that no longer exist, which would blossom into the wider discipline of paleontology. Buckland's description of Megalosaurus came at a time when fossil hunting and geology were booming pursuits. Across Europe, scientists and amateur fossil collectors were uncovering bits and pieces of prehistoric life, but it was the painstaking effort to put pieces together, sometimes literally, that created the first skeletal reconstructions, like Megalosaurus, bridging the ancient past and modern science. The significance goes beyond pure science as well. Megalosaurus appeared in early artistic reconstructions during the Victorian era, often depicted in museums and literature as a fearsome beast, a symbol of a vanished world that kindled the public's imagination. Such depictions helped foster an enduring fascination with dinosaurs that continues to this day. Buckland himself continued to be an active figure in geology and paleontology, contributing to various discoveries and debates. But it was this groundbreaking work on Megalosaurus that remains one of his lasting legacies. His publications were widely circulated, sparking enthusiasm and discussion among scientists and laypeople alike. It is important to remember that scientific knowledge in Buckland's day was limited compared to what we have now. For instance, early skeletal reconstructions were often inaccurate in posture and proportion, sometimes reflecting the biases of the time rather than the reality of the animal's form. Megalosaurus reconstructions showed it as a sprawling reptile, somewhat like a giant lizard, which we now know is imprecise. But this early interpretation was a crucial first step in a much longer journey. Today, Megalosaurus continues to be recognized not only as the first dinosaur-bearing genus to be scientifically described, but as a symbol of a pivotal shift in how human beings began to comprehend Earth's deep past. Through Buckland's meticulous work, the shadowy outlines of prehistoric beasts were fleshed out into articulated skeletons, display cases, and scientific truths. This laid the groundwork for succeeding generations of paleontologists to explore, discover, and piece together the myriad dinosaur species that once walked the Earth. As our narrative progresses through the history of dinosaur discoveries, it is essential to acknowledge this milestone, one that transformed mysterious fossil fragments into the tangible evidence of creatures that roamed the Earth millions of years ago. The revelation of Megalosaurus by William Buckland is a tale of curiosity, dedication, and the dawning of a scientific era that would eventually reshape our understanding of the natural world and our own place within its long history. From Buckland's early 19th century investigations in an English quarry to the vast fossil beds of subsequent decades, the quest to uncover and understand dinosaurs has been filled with moments of wonder and revelation. Megalosaurus was, in many ways, the key that unlocked the door to this prehistoric world, inviting humanity to step beyond the bounds of its own time and glimpse the marvels of deep time. This journey now naturally unfolds towards another remarkable pioneer, Mary Anning, whose discoveries beneath the cliffs of Lyme Regis would continue to expand the prehistoric panorama far beyond terrestrial giants like Megalosaurus into the strange and enchanting marine reptiles that swam the ancient seas. But before we follow that current, let us savor the profound beginnings sparked by Buckland's dedicated work and the skeleton of Megalosaurus that first roared to life in the halls of science. In the early 19th century, not long after William Buckland's pivotal work on Megalosaurus began to unveil the ancient past buried beneath England's soil, the coastal cliffs of Lyme Regis on the English Channel became the stage for a different kind of revelation, one that would open the scientific world's eyes to an entirely new dimension of prehistoric life: the ancient seas. Our story now turns to Mary Anning, a remarkable fossil hunter and paleontologist whose tireless work unearthed some of the most extraordinary marine reptile skeletons ever discovered, altering forever humanity's understanding of the deep, ancient oceans and their mysterious inhabitants. Mary Anning was born in 1799 in Lyme Regis, a small seaside town famous for its geology and the abundance of fossils embedded in the cliffs along the Jurassic coast. This rugged coastline, shaped by eons of geological upheaval and erosion, revealed spectacular fossil remains that had long drawn the attention of local collectors and curious visitors. Mary's family was modest. Her father was a cabinet maker and carpenter, but they eked out a living by collecting and selling fossils to visitors and scientists alike. From a young age, Mary displayed an extraordinary talent for finding and extracting fossils, a skill that grew with experience amid the fossil-rich shale and limestone. The early 19th century was a time when scientific understanding of prehistoric life was still very fragmented. Although Buckland and a few others had begun interpreting terrestrial fossils as the remains of long-extinct creatures, the idea that oceans once hosted giant, unfamiliar reptiles was revolutionary. Yet the fossils Mary uncovered from the cliffs told an astonishing story of marine reptiles much larger and stranger than anything alive today. In 1811, when Mary was just 12 years old, she and her brother Joseph discovered the first complete ichthyosaur skeleton. Ichthyosaurs were dolphin-like reptiles with sleek, streamlined bodies adapted to life underwater. Their discovery electrified the scientific community. This was the first time a nearly complete specimen had been found, allowing for a comprehensive study that would reveal previously unimaginable creatures swimming the prehistoric seas during the Jurassic period, roughly 200 million years ago. The ichthyosaur skeleton was unlike anything known at that time. Its long jaws filled with conical teeth, its massive eye sockets adapted for keen underwater vision, and its paddle-like limbs were all clues to its aquatic lifestyle. Mary's meticulous excavation and reconstruction provided a window into a world lost for millions of years. The discovery challenged old ideas and bolstered the emerging field of paleontology, providing concrete evidence that Earth's history was far more complex and fascinating than anyone had imagined. Mary's contributions did not stop with ichthyosaurs. In 1823, she unearthed an equally extraordinary skeleton that would come to be known as Plesiosaurus. The plesiosaur was a marine reptile quite different from the ichthyosaur. With a broad body, 4 powerful flipper-like limbs, and an incredibly long neck crowned by a small head, it looked stranger and more enigmatic. Its unique anatomy baffled scientists and fascinated the public, inspiring countless studies. The long-necked plesiosaurs painted a vivid picture of marine ecosystems that had little parallel in the modern oceans. What made Mary Anning's discoveries groundbreaking was not only their completeness, but also how they expanded the very notion of prehistoric life. They showed that the Mesozoic seas were teeming with giant reptiles that bore little resemblance to modern marine animals, highlighting the vast evolutionary history hidden beneath layers of rock. Her fossils bridged a gap between Earth and ocean, illuminating an ancient era that lay just beyond the horizons of contemporary knowledge. Mary's work was not without challenges. As a self-taught scientist and a woman in an era when upper-class men dominated the scientific establishment, she often faced prejudice and was frequently overlooked in scientific circles. Though many prominent geologists and paleontologists studied her fossils and published papers acknowledging their importance, Mary's role was often diminished or uncredited. Nevertheless, her expertise was undeniable, and her field intuition was unmatched. She understood the cliffs and the conditions that led to fossil preservation. She mastered the delicate art of excavation, carefully removing fossils embedded in fragile rock, often at great personal risk from landslides and dangerous cliff faces. Her unyielding dedication helped reveal thousands of specimens, some of which were used by leading scientists to describe new species and develop evolutionary theories long before Darwin's On the Origin of Species. Among the fascinating details of her finds was the evidence of soft tissue impressions alongside the bones, which provided rare insights into the skin and body structures of these ancient reptiles. Such findings challenged assumptions that fossils were merely petrified bones and opened doors to the study of anatomy and function rather than just form. Mary Anning's discoveries also influenced the popular imagination and culture. Plesiosaurs and ichthyosaurs became staples in the growing collection of prehistoric creatures, showcased in museums and illustrated in popular books and periodicals. These marine reptiles fueled myths and legends about sea monsters, while also grounding those ideas in scientific observation. Importantly, her work helped set the stage for understanding the profound changes Earth's ecosystems have undergone. The Mesozoic seas she uncovered belonged to a lost world of biodiversity and complexity, emphasizing the dynamic nature of life on our planet over geological time spans. Her legacy lives on not only in the fossils preserved in natural history museums, but also in the very foundations of paleontology as a science. Mary Anning is often regarded as one of the first and most successful fossil hunters, a pioneer who opened a window onto prehistoric marine life. She showed the world that even in the jagged edges of limestone cliffs, there existed stories of astonishing creatures that, for a time, ruled the seas. As we trace this unfolding tale of dinosaur discovery, Mary Anning's work invites us to peer deeper beneath the waves and recognize that the history of life on Earth is as much about oceans as it is about land. With her finds of ichthyosaur and plesiosaur skeletons, she helped paint a fuller picture of the Mesozoic world, a world where massive reptiles swam in primeval seas long before the reign of the great terrestrial dinosaurs was truly understood. This story of exploration and discovery naturally flows onward to another iconic figure of the era, Gideon Mantell, whose partial discovery of Iguanodon would ignite a fervor of dinosaur fascination in Victorian Britain. But before we travel there, it is worth lingering in the coastal winds of Lyme Regis, where Mary Anning's legacy first stirred the ancient seas to life for modern eyes, linking the deep past to the dawn of modern paleontology. As we transition from the sweeping marine discoveries made by Mary Anning along the jagged cliffs of Lyme Regis, our journey now takes us inland to the gentle rolling hills of Sussex, England, where another pioneering figure emerged to ignite a fervor for dinosaur discovery and significantly influence Victorian science and culture. Gideon Mantell, a country doctor turned avid fossil collector, became a key protagonist in one of the earliest and most remarkable chapters in paleontology through his unearthing and study of the partial skeleton of Iguanodon, a find that helped birth what would soon be known as dinosaur fever, a cultural and scientific phenomenon that captivated Britain during the 19th century. Born in 1790, Mantell was not formally trained as a professional scientist, but his passion for geology and fossils ran deep from an early stage. His work as a physician in the rural areas of Sussex provided the opportunity to explore nearby quarries and chalk pits, enriching his natural history pursuits alongside his medical practice. At that time, fossils were still somewhat of a novelty and frequently misunderstood, yet Mantell's keen eye was destined to change that. The story of the Iguanodon begins with the discovery of large fossilized teeth in 1822 within a quarry at Whiteman's Green, near Cuckfield. Mantell's interest was piqued, and after studying the teeth carefully, he noted their remarkable resemblance to the teeth of modern iguanas, but far larger and more robust. Hence the name Iguanodon, meaning iguana tooth. This was the first time a fossil tooth had prompted such a precise and reasoned link to a living reptile, setting a new standard for paleontological identification. However, it was not until 1825 that Mantell found more substantial skeletal remains, including parts of the iguanodon's jaw, vertebrae, and other bones. These fragments, although partial and scattered, were enough to reconstruct a rough image of a large herbivorous reptile that once roamed prehistoric landscapes. Mantell carefully compared the bones to modern reptiles and mammals, trying to piece together the creature's appearance and habits. One of the more fascinating elements of Mantell's reconstruction was his interpretation of the Iguanodon's thumb. Early on, because of the shape of the thumb bones, he proposed that it was a large spike, perhaps used as a defensive weapon. This idea, while later modified, illustrated the difficulties and creativity required to reconstruct completely unknown extinct creatures from fossil fragments. This thumb spike became iconic in early depictions of dinosaurs and helped solidify the iguanodon as a symbol of Dinosauria's strange and exotic nature. Mantell's work occurred in a vibrant scientific environment where the concept of extinction was gaining acceptance but was still debated. Demonstrating that creatures like Iguanodon had once lived but no longer did was a crucial contribution to shifting the collective understanding of Earth's history. Mantell was not alone in his endeavors, however. His discoveries closely followed William Buckland's work on Megalosaurus and fed into the growing public and scientific interest in prehistoric reptiles. Yet Mantell's ability to communicate and promote these finds brought a new level of excitement. His detailed writings and illustrations, combined with the vivid imagination they sparked, caught the attention of both scholars and the Victorian public alike. Unfortunately, Mantell's career was beset by financial difficulties and personal challenges. Despite his significant contributions, he struggled for recognition and support, sometimes losing ground in disputes with professional competitors. Nevertheless, his passion never waned, and his persistence helped anchor dinosaurs as a legitimate and thrilling scientific pursuit. The cultural impact of Mantell's Iguanodon was profound. Around this time, geological societies proliferated, natural history museums expanded their fossil collections, and public lectures began to herald the wonders of the prehistoric past. Iguanodon, along with Megalosaurus and Hylaeosaurus, a third genus identified around the same period, formed the foundation of the new Dinosauria group, a term proposed in 1842 by Sir Richard Owen, formalizing the recognition of this distinct group of ancient reptiles. These discoveries fueled the imaginations of the Victorian public, inspiring fascination with monstrous reptiles that roamed vast primeval forests and swam ancient seas. They also contributed to scientific debates on evolution, extinction, and the planet's dynamic history. Mantell's role as a pioneering figure symbolizes more than just fossil discovery. He embodies the passionate amateur scientist's place in the development of paleontology. His work bridged the realms of medicine, geology, and emerging evolutionary theory, while his particular discovery of the partial iguanodon skeleton was instrumental in catalyzing widespread interest in dinosaurs. The iguanodon became a cornerstone of gazing back in time, to a world unimaginable just decades prior. Today, Iguanodon is recognized as one of the first dinosaurs ever scientifically described and among the best-known early examples. Modern discoveries have vastly expanded our understanding of this genus, showing it to be a large plant-eating dinosaur with complex behaviors. But Gideon Mantell's pioneering identification and reconstruction remain a landmark moment. It marked a shift in how people imagined the past and laid the groundwork for the dinosaur discoveries and debates that would follow with ever-increasing energy and excitement. From the partial skeleton Mantell excavated in the chalk pits of Sussex emerged a public fascination that helped fuel great museum exhibitions, scientific inquiry, and even artistic renderings of what prehistoric life might have looked like. It is here that dinosaur science began to take hold, not only in academic circles, but also in the popular imagination. With Mantell's contribution firmly established, the stage is set for even more sensational discoveries and the evolution of dinosaur paleontology as a cultural phenomenon. The next major scene unfolding at Bernissart, Belgium, where a buried herd of iguanodon skeletons would reveal the early potential for mounted dinosaur skeletons and spectacular fossil assemblages. But for now, we pause to appreciate the spark that Mantell ignited in Victorian Britain, a primal story of scientific curiosity and the relentless quest to reconstruct the ancient past from the echoes left in stone. In the midsummer of 1878, a remarkable discovery rippled through the scientific community and profoundly shaped the way dinosaurs were understood and exhibited for generations to come. This discovery was made deep underground in the coal mines of Bernissart, a small town in Belgium's Hainaut province. What miners initially encountered buried beneath layers of rock would soon be known as the Bernissart Iguanodons, a spectacular herd of dinosaur skeletons preserved together in a natural time capsule. This find did more than add hundreds of bones and a dozen articulated skeletons to the fossil record. It marked the birth of mounted dinosaur skeletons and transformed public engagement with prehistoric life in an unprecedented fashion. The Bernissart coal mine, about 322 meters, over 1,000 feet, below the surface, was a complex labyrinth of shafts and tunnels where miners had been extracting coal for decades. On August 1878, workers stumbled upon large fossilized bones embedded in a layer of sedimentary rock. Word of the strange finds quickly reached paleontologists, and soon Louis Dollo, a renowned Belgian paleontologist, was called to investigate this extraordinary occurrence. The scale of the find was staggering. Dozens of almost complete Iguanodon skeletons, many of them remarkably well preserved and articulated, lying side by side as though they had been herd members tragically buried by a sudden natural event millions of years ago. These skeletons, encased in stone and carefully extracted over months, provided the most comprehensive insight yet into the structure and social behavior of these herbivorous dinosaurs, dating to the early Cretaceous period, approximately 125 million years ago. Prior to Bernissart, dinosaur fossils were primarily fragmentary, hard to interpret, and presented as isolated bones or incomplete skeletons. The simultaneous discovery of a group of individuals was revolutionary. It suggested that dinosaurs might have lived and moved in social groups, challenging earlier ideas of solitary reptilian creatures. This insight opened new avenues of research into dinosaur ecology and behavior. Yet, perhaps the most profound legacy of the Bernissart discovery was the pioneering effort led by Louis Dollo to mount the Iguanodon skeletons for public display. This was a groundbreaking undertaking. Previously, fossils were typically exhibited as scattered bones or partial reconstructions. Dollo's vision to assemble full skeletons in lifelike standing poses was inspired both by scientific curiosity and the desire to enthrall viewers with a vivid glimpse into the prehistoric past. Mounting the skeletons was a challenge without modern methods or materials. Dollo and his team painstakingly recreated the anatomy of Iguanodon, guided by the exceptional completeness of the fossils and comparative study with existing reptilian anatomy. They innovated metal frameworks to support the fossils, positioning the skeletons upright to hint at a dynamic, living creature rather than a static collection of bones. One notable feature was the reinterpretation of the Iguanodon's thumb spike. Earlier views imagined it as a horn placed on the nose of the dinosaur, but Dollo demonstrated it belonged to the hand and likely served defensive purposes, reshaping the dinosaur's silhouette and internal anatomy in museum halls. These mounts were first commissioned for the Royal Belgian Institute of Natural Sciences in Brussels, where they captivated both scientists and the general public alike. Seeing these life-sized sculptures, reconstructed from real fossil bones, stirred the imagination of visitors and solidified dinosaurs' place in both science and culture. It was the beginning of an enduring tradition of dinosaur mounts that continues to be a central feature of natural history museums worldwide. The discovery from Bernissart also spurred scientific studies that deepened our understanding of dinosaur growth, health, and population dynamics. The uniformity of the herd, the age ranges between specimens, and preservation conditions ignited discussions on dinosaur mortality events, herd behavior, and paleo-environments. Moreover, the Bernissart iguanodons indirectly influenced prominent figures in paleontology and museum curation, inspiring similar excavations and museum displays across Europe and later in North America. This herd was a clear illustration of the power of fossils to narrate ancient stories and was a catalyst for the intense dinosaur mania sweeping through Victorian society. In the years following the Bernissart discoveries, mounting dinosaurs became a prestigious scientific art form. Museums began to compete in presenting the most accurate and awe-inspiring dinosaur exhibits. The Bernissart herd stood as a model of what could be achieved when science, artistry, and education converged. Today, replicas and some of the original Bernissart fossils remain centerpieces in museums, not just in Belgium, but globally, serving as a reminder of the transformative power of that coal mine's buried secret. The Bernissart iguanodons symbolize the moment when dinosaurs emerged not only from stone, but into the living imaginations of millions, firmly embedding prehistoric giants in the collective consciousness. This monumental find and the innovation of mounted dinosaur display set the stage for further iconic skeletons that would later travel across continents and inspire public awe, such as the famous Diplodocus carnegii, whose story we will explore next. But before the era of gigantic sauropods taking center stage, it is important to appreciate how a herd of iguanodons, buried in a deep Belgian mine, awakened the world to the majestic reality of these ancient creatures whose bones told tales of a lost age and brought the past vividly to life. As we follow the unfolding tale of dinosaur discoveries from the early Victorian enthusiasms in England and Belgium, the story crosses the Atlantic to the United States in the late 19th century, where an extraordinary fossil find would captivate the world and inaugurate a new era in the popularization of dinosaurs. This is the story of Diplodocus carnegii, a long-necked dinosaur whose spectacular skeleton and the influential patronage of industrialist Andrew Carnegie transformed public fascination and scientific appreciation for these ancient giants. Diplodocus, meaning double beam, for its distinctive double-beamed tail vertebrae, was a gigantic sauropod dinosaur that roamed the western United States during the late Jurassic period, about 150 million years ago. Though sauropods had been known from earlier discoveries, none had yet captured the public imagination like the finds uncovered during the American Bone Wars, a fiercely competitive period of paleontological exploration and rivalry between Edward Drinker Cope and Othniel Charles Marsh. In 1897, an expedition led by Carnegie Museum paleontologist John Bell Hatcher unearthed one of the most complete Diplodocus skeletons near Sheep Creek, Wyoming. This specimen was promptly named Diplodocus carnegii, in honor of Andrew Carnegie, the wealthy industrialist and philanthropist who generously funded the expedition and the museum itself. Carnegie's patronage was pivotal not only for the excavation, but also for how the dinosaur was subsequently promoted to the public. A man of grand vision, Carnegie saw the power of science and culture hand in hand and believed in using his wealth to educate and inspire. He viewed the display of a life-sized dinosaur skeleton as a means of awe-inspiring not only the scientific community, but also everyday museum visitors who could marvel at the scale and mystery of prehistoric life. The Diplodocus carnegii skeleton was meticulously prepared and mounted in 1907, standing as the centerpiece of the Carnegie Museum of Natural History in Pittsburgh. Measuring over 85 feet, 26 meters in length, It was one of the longest dinosaur skeletons assembled to date. Its graceful, sweeping neck and tail, along with its massive, pillar-like legs, presented an unforgettable image of prehistoric grandeur. But Carnegie's ambitions extended far beyond a single museum display. Understanding the diplomatic and educational potential, he commissioned the creation of several exact copies of the mounted Diplodocus skeleton, which were then gifted to prestigious museums around the world, including the Natural History Museum in London, the French National Museum of Natural History in Paris, and the Museum of Natural Sciences in Madrid. This act fostered an early form of international scientific and cultural exchange centered on dinosaur fascination. The public reaction to these mounted Diplodocus skeletons was phenomenal. For many, this was the first opportunity to witness the physical form of a dinosaur at life size, providing a visceral connection to Earth's distant past. The displays stimulated immense curiosity and enthusiasm, capturing headlines and inspiring art, literature, and education. Scientifically, Diplodocus carnegie's skeleton allowed researchers to refine their understanding of sauropod anatomy, posture, and biomechanics. Early reconstructions depicted the dinosaur with a sprawling, tail-dragging stance, but subsequent studies revealed a more balanced, elevated posture where the tail was held aloft as a counterweight to the long neck, enhancing mobility and grace. Carnegie's role as a philanthropist was emblematic of a broader pattern in this era, where wealthy patrons significantly advanced paleontology's reach and stature. His commitment to funding expeditions, museum curation, and public education helped set a precedent for the integral relationship between science and society, a relationship that remains vital today. Moreover, the iconic status of Diplodocus carnegii influenced popular culture widely. From children's books to exhibitions, films to scientific literature, dinosaurs became synonymous with wonder and discovery. The Diplodocus casts helped demystify prehistoric life, shaping public perception and fostering a sense of shared heritage and curiosity about Earth's history. The story of Diplodocus carnegii and Andrew Carnegie's visionary patronage is a testament to how science, art, and philanthropy can intertwine to elevate knowledge and inspire millions. It illustrates a key moment when the age of dinosaurs transitioned from academic curiosity to cultural phenomenon, embedded in museums and imaginations worldwide. As the remarkable journey of dinosaur discoveries continues, the narrative moves forward to another extraordinary fossil find: the Dueling Dinosaurs of Montana, a spectacular and mysterious skeleton that captures a moment frozen in time. But before stepping into the American West again, we pause to reflect on how Diplodocus carnegii, through careful scholarship and generous support, bridged continents and cultures, ensuring dinosaurs would forever roar not only in the depths of the Earth's past, but also in the hearts of people around the world. In the vast, rugged landscapes of Montana, a region renowned for its rich deposits of late Cretaceous fossils, an extraordinary discovery was made that would capture the imagination of scientists and dinosaur enthusiasts alike. This find, known colloquially as the Dueling Dinosaurs, is a spectacular and mysterious fossil assemblage that literally froze two prehistoric creatures locked in combat some 75 million years ago. Unearthed in 2006 near the small town of Glendive, this fossilized snapshot offers a tantalizing glimpse into the behavior, ecology, and visceral realities of the dinosaurian world during the twilight of the age of dinosaurs. The dueling dinosaurs are a remarkably preserved pair: a Tyrannosaurus rex, the iconic apex predator of the late Cretaceous, and a smaller but no less formidable herbivore, the Triceratops horridus, distinguished by its three impressive facial horns and bony frill. What makes this fossil so unique is their intertwined skeletal remains, embedded in the sandstone matrix, suggesting some form of close interaction, possibly the final moments of a deadly encounter where predator met prey and both were entombed together before fossilization could separate their fates. This exceptional preservation is unparalleled in paleontology. While many fossil sites reveal isolated skeletons or groupings of animals, rarely do we find two different species seemingly caught in the throes of combat. The completeness of the fossils, virtually 100% of both skeletons is preserved with exquisite detail, adds to their scientific and public appeal, providing an unprecedented resource for understanding dinosaur anatomy, skin texture, and even potential soft tissue impressions. The story behind the discovery is one of persistence and intrigue. The dueling dinosaurs were uncovered by Montana rancher Clayton Phipps, who recognized their significance early on and ensured their protection. However, the fossils became the subject of a complex legal and financial saga involving private ownership claims, scientific accessibility, and debates over their ultimate fate, whether they would become publicly studied specimens or remain in private hands. Because of these ownership issues, the fossils remained largely inaccessible to scientists for several years despite their immense importance. This has fueled a sense of anticipation within the scientific community about the insights they could yield once fully studied and prepared. Scientifically, these fossils offer the possibility to answer long-standing questions about T-Rex anatomy and behavior. For example, the position of the skeletons could reveal evidence of predation strategies and defensive maneuvers of Triceratops, while the exceptional bone preservation raises hopes of studying growth patterns, pathology, and possibly even traces of pigmentation or soft tissue structures. Moreover, the dueling dinosaurs have drawn attention to the interactions between predator and prey species in the late Cretaceous ecosystem, enriching our understanding beyond skeletal form to behavior and ecology. This fossilized battle scene is a unique window into life and death 75 million years ago. The site also illuminates the broader context of fossil preservation in Montana's Hell Creek Formation, a geologic treasure trove that has produced many of the most famous dinosaur specimens, including some of the most complete and studied T-Rex finds alongside numerous ceratopsians, hadrosaurs, and other Cretaceous taxa. The dueling dinosaurs stand out as a rare, almost cinematic time capsule, linking these great beasts in dramatic confrontation. Beyond the scientific realm, the specimens have inspired museum exhibits, documentaries, and public fascination, reinforcing the deep connection humans feel to these prehistoric giants. They embody the mysteries and marvels still waiting to be uncovered in the fossil record. As we anticipate the eventual full scientific unveiling of the dueling dinosaurs, their story seamlessly connects the pioneering discoveries of past centuries with today's cutting-edge research and public engagement. Their frozen combat links us directly back to the fierce dynamics of the ancient past, reminding us that beneath Montana's modern landscapes lie silent stories etched in stone and bone, waiting patiently to reawaken. From these epic moments in Montana, our story will next explore Sioux, the world's most complete Tyrannosaurus rex skeleton, an equally remarkable find that has redefined our understanding of T-Rex anatomy and pathology. But before we follow that path, the tale of the dueling dinosaurs invites us to reflect on how even in the rocky silence of fossilized remains, the drama and life of the Mesozoic radically persist across time, continuing to enthrall and educate generations. Among the myriad dinosaur discoveries that have enthralled scientists and the public alike, few have captured the imagination as vividly as Sioux, the world's most complete and remarkably preserved Tyrannosaurus rex skeleton. Unearthed in the late 20th century, Sioux reignited and deepened our understanding of this colossal predator and profoundly influenced paleontology, museum curation, and popular culture. The story of Sue begins in the summer of 1990 on the Cheyenne River Indian Reservation near Faith, South Dakota. Sue Hendrickson, an accomplished fossil hunter and explorer, was leading an expedition when she stumbled upon a large fossil protruding from a cliff face. As excavation proceeded under the guidance of paleontologist Peter Larson and his Black Hills Institute team, it became clear that what they had uncovered was extraordinary. A nearly 90% complete T-Rex skeleton, one of the most intact specimens of its kind ever found. The skeleton comprised about 250 bones, including the skull, vertebrae, ribs, limbs, and elusive parts like forearms and parts of the pelvis. The completeness and preservation of Sue were unparalleled. The bones were robust, yet displayed a wealth of detailed features, bite marks, injuries, and evidence of diseases that told a vivid story beyond mere anatomy. This specimen offered an unprecedented opportunity to study the anatomy, physiology, and life history of Tyrannosaurus rex, one of the largest carnivores to ever walk the earth. Excavating Sue was no small feat. The fossil was encased in a hard sandstone matrix atop a remote ridge, requiring meticulous and painstaking efforts over several months to free the bones without damage. The team used jackets of plaster to protect the bones during transport and scientific preparation, a testament to the challenges of paleontological fieldwork. Once in the laboratory, the painstaking process of cleaning, preserving, and assembling the skeleton began, which would take many years. However, Sue's story extended beyond science. Legal battles erupted over ownership of the fossil between the Black Hills Institute, the landowner, the U.S. government, and the Sioux tribe, in whose reservation the bones were found. After a protracted court case, the fossil was seized by the federal government and later auctioned by Sotheby's in 1997. The Field Museum of Natural History in Chicago purchased Sue for $836 million, with major financial backing from corporations, including McDonald's and Disney, underscoring the cultural significance attached to this remarkable specimen. Once mounted on display, Sue became an instant icon. Standing over 12 feet tall at the hips and nearly 40 feet long, with a skull roughly 5 feet long, the largest ever discovered, Sue towers as an awe-inspiring testament to nature's grandeur and the deep past. The specimen's articulation and lifelike pose provide visitors with a vivid impression of T-Rex as a powerful predator, poised and imposing. Scientific studies of Sue have yielded invaluable insights. Detailed CT scans and biomechanical analyses have revealed information about T-Rex's growth rates, feeding behavior, sensory capabilities, and even the impact of injuries during its life. For example, Sue's skull tells of healed bite wounds potentially inflicted during combat with other T-Rex individuals, highlighting the aggressive and competitive nature of these gigantic carnivores. Furthermore, Sue's exceptional preservation allowed investigations into pathologies and bone diseases never before seen in such detail in dinosaurs. Analysis of bone microstructure has provided clues about metabolism and growth, suggesting that T-Rex may have grown rapidly during adolescence, much like modern birds and mammals. Beyond scientific achievement, Sue's public display has had profound cultural and educational impacts. The skeleton has drawn millions of visitors worldwide, fostering widespread fascination with dinosaurs and paleoscience. Children and adults alike have been inspired to learn about evolutionary history, ecology, and Earth's geological past. Museums worldwide have used Sue's success as a model for mountings and exhibits, emphasizing accuracy and immersive presentation. The specimen helped catalyze a renaissance in paleontological exhibits, blending rigorous science with engaging storytelling to appeal to broad audiences. Sue's discovery also invigorated debates about dinosaur behavior physiology, and ecology, leading to more dynamic and nuanced interpretations of these ancient creatures. Rather than static, lumbering monsters, modern views shaped by specimens like Sue depict T-Rex as a complex, active apex predator with intricate social and ecological roles. The tale of Sue also serves as a potent reminder of the challenges and sometimes controversies that accompany fossil discoveries in modern times, involving legal, ethical, and cultural considerations about land rights, fossil ownership, and scientific access. From the cliffside discovery in South Dakota to her majestic display in Chicago's Field Museum, Sue remains a landmark in paleontology. Her bones whisper tales of a world long vanished, yet continue to inspire, educate, and captivate those who seek to understand the grandeur and mystery of the age of dinosaurs. As we continue our exploration of groundbreaking fossil finds, the next chapter leads us to Archaeopteryx, the feathered fossil that profoundly altered our understanding of the evolution of birds and dinosaurs. But before we delve into that feathered connection, we pause to appreciate Sue's formidable legacy. A pinnacle of fossil discovery that beautifully melds science, culture, and timeless wonder. As our journey through dinosaur discoveries unfolds, we arrive at one of the most transformative scientific revelations, one that blurred the boundaries between reptiles and birds, fundamentally reshaping our understanding of evolution and the origin of flight. This revelation centers around Archaeopteryx, a fossil so extraordinary that its uncovering in the mid-19th century sparked debates and fascination that continue to influence paleontology and ornithology today. The tale begins in 1861 in the limestone quarries of Solnhofen, Bavaria, Germany. This region, well known for its exceptionally fine-grained Jurassic limestone deposits, formed about 150 million years ago during the late Jurassic period and created ideal conditions for preserving delicate fossils in astonishing detail. The Solnhofen Lagoon environment was a shallow, warm, stagnant sea, with fine sediment that gently buried and preserved organisms, some with impressions of feathers and soft tissues rarely fossilized elsewhere. Against this unparalleled backdrop, a fossil hunter uncovered a remarkable specimen, a small creature that bore the unmistakable imprint of feathers alongside a skeletal structure showing a mixture of both reptilian and avian traits. This specimen would come to be known as Archaeopteryx lithographica, meaning ancient wing drawn on limestone. The anatomical features of Archaeopteryx were both baffling and enlightening. It possessed wings and feathers nearly identical to those of modern birds, indicating it was capable of flight or at least gliding. Yet its skeleton retained unmistakably reptilian features: sharp teeth embedded in jaws, 3 clawed fingers on each wing, a long bony tail, and certain pelvic and skull characteristics typical of theropod dinosaurs. This combination placed Archaeopteryx in a pivotal position between birds and reptiles. The timing of its discovery, a year after Charles Darwin published On the Origin of Species in 1859, added profound significance. Archaeopteryx was quickly hailed as the enigmatic missing link, providing critical fossil evidence to support evolutionary theory by illustrating a transitional form between 2 major groups of vertebrates. This finding validated the concept that species could evolve over time, changing only small traits, yet eventually producing monumental biological transformations. The story of Archaeopteryx also highlights the evolving methodologies and interpretations in early paleontology. Early reconstructions depicted it as a primitive bird, often perching and flapping in ways familiar to modern birds, but the presence of claws and teeth challenged straightforward classification. It took decades of comparative anatomy, fossil discoveries, and advances in cladistics to situate Archaeopteryx firmly as an early bird, sharing a common ancestor with small, feathered theropod dinosaurs. Beyond its anatomical magic, Archaeopteryx left a substantial imprint on scientific and public imagination. Feathers, a feature once thought uniquely avian, were now known to have deeper evolutionary roots tied to dinosaurs. This revelation has been confirmed and expanded in recent decades by discoveries of feathered dinosaurs in China's Liaoning province and elsewhere, further solidifying birds as living dinosaurs, a lineage that remarkably survived the cataclysmic extinction event 66 million years ago. The specimen itself became one of the most treasured fossils in the paleontological world, with several Archaeopteryx specimens unearthed over time. These fossils often bear delicate feather impressions preserved alongside bones, providing unmatched insights into the structure, coloration patterns, and potential functions of feathers in early avian evolution. Intriguingly, the Solnhofen limestone's unique preservation has given scientists clues beyond skeletal anatomy. Some specimens reveal details of feather arrangement akin to modern flight feathers, including asymmetry, crucial for aerodynamic lift. Other clues hint at behaviors such as predation or arboreal lifestyle, informing models of how flight might have evolved, not simply as powered flapping, but possibly from gliding or maneuvering through trees. Archaeopteryx's discovery also underscored the importance of fossil context. Without the exceptional conditions of Solnhofen's fine-grained limestones, such spectacular preservation of feathers and subtle anatomical details would have remained elusive. This has encouraged paleontologists to seek similar Lagerstätten, or fossil deposits of extraordinary preservation, around the globe. Moreover, Archaeopteryx stands as a symbol of scientific progress, how new evidence can challenge existing paradigms and enrich our understanding of life's complex history. From confusion and skepticism arose clarity and acceptance. Birds are not just distant descendants of dinosaurs, but are themselves the last living clade of that great extinct group. This revelation elegantly narrates a continuous thread tying the present to deep time. As we transition to the Gobi Desert expeditions led by Roy Chapman Andrews and the discovery of Protoceratops and Velociraptor fossils, it is important to acknowledge Archaeopteryx's role in broadening the paleontological horizon. It illuminated the evolutionary bridge and spurred the search for more feathered dinosaurs, culminating in the explosive fossil revelations of the late 20th and early 21st centuries. The discovery of Archaeopteryx continues to inspire curiosity and wonder. A feathered ambassador from a world that saw the dawn of flight, reminding us that scientific discovery is a journey of connecting fragments across ages to glimpse the marvelous tapestry of life on Earth. As the 20th century dawned, the arid and enigmatic Gobi Desert in Central Asia became the setting for some of the most thrilling and scientifically significant dinosaur discoveries ever made. This remote landscape, seemingly desolate and harsh, concealed extraordinary windows into the Cretaceous period, particularly through the expeditions led by Roy Chapman Andrews, an intrepid American explorer and paleontologist whose daring journeys would uncover iconic fossils like Protoceratops and Velociraptor, forever transforming our understanding of dinosaur diversity, behavior, and evolution. Roy Chapman Andrews, often described as a real-life Indiana Jones before the fictional adventurer's time, spearheaded the Central Asiatic expeditions of the American Museum of Natural History beginning in the 1920s. Motivated by scientific curiosity and a zeal for exploration, Andrews and his team ventured into uncharted territories of Mongolia's Gobi Desert, battling extreme climate, rugged terrain, and logistical challenges. The Gobi Desert's Badlands proved to be a paleontological treasure trove, rich in sedimentary rock formations dating back approximately 75 million years to the late Cretaceous. It was within these layers that the expedition made groundbreaking discoveries, most notably the nearly complete skeletons of Protoceratops and Velociraptor. Protoceratops was a sheep-sized herbivorous dinosaur resembling a smaller cousin of the famously horned and frilled ceratopsians. Its fossils uncovered in the Gobi displayed the characteristic large frill and beak-like mouth, indicating adaptations for cropping vegetation. These specimens provided priceless insights into ceratopsian anatomy and hinted at their social behaviors, possibly moving in herds much like modern grazing animals. Velociraptor, by contrast, was a small but fearsome predatory theropod dinosaur with a lightly built bipedal frame, an enlarged sickle-shaped claw on each foot, and an agile, intelligent appearance suggested by the structure of its brain case. Discoveries of these skeletons, including skulls, claws, and even remnants that suggested feathers, captured imaginations worldwide and challenged earlier conceptions that dinosaurs were sluggish, cold-blooded reptiles. One of the most iconic finds from these expeditions was the famous Fighting Dinosaurs fossil, discovered later in the same region, which preserved a velociraptor locked in combat with a protoceratops, a dramatic snapshot of predator and prey frozen in time, underscoring the violent realities of prehistoric life. This discovery, though somewhat later, ties directly back to the foundation laid by Andrews and his team. These discoveries played a key role in shifting scientific perspectives during the early 20th century. The complex anatomy, inferred behavior, and even the possibility of feathers on velociraptors suggested evolutionary links between dinosaurs and modern birds, a hypothesis that would be substantiated decades later but was first tantalizingly supported by these findings. Moreover, Andrews's expeditions brought global attention to Mongolia's fossil heritage and sparked further paleontological research across Asia, a region that has since yielded some of the richest dinosaur fossil beds in the world. The expeditions were not just about scientific discovery, they were cultural exchanges, pioneering archaeology, and bold adventures into the unknown. The legacy of the Gobi Desert expeditions extends beyond the fossils themselves. Andrews became a symbol of adventurous science, coalescing public interest in dinosaurs with compelling stories of exploration. His findings fostered an appreciation for the diversity and complexity of dinosaur ecosystems and paved the way for modern paleontological techniques using systematic excavation and detailed analysis. As we look ahead, the mysterious and long-necked giants revealed by Chinese dinosaur digs, the Mamenchisaurus and related sauropods, continue this exciting journey through dinosaur discoveries in Asia. But before we venture there, the Gobi Desert stands as a monument to how audacity, meticulous science, and the spirit of discovery combine to illuminate our planet's distant past in vivid and lasting detail. As our narrative of dinosaur discovery unfolds across continents and centuries, we now turn our gaze eastward to one of the most remarkable chapters in paleontology, the ongoing dinosaur excavations in China, a region that has steadily revealed some of the most fascinating and well-preserved long-necked giants ever found. Central among these is Mamenchisaurus, a genus whose extraordinary size and graceful neck continue to inspire awe, and whose discovery exemplifies the resilience and perseverance of Chinese dinosaur research that has transformed the global scientific understanding of sauropod evolution. Mamenchisaurus, whose name translates to Mamenchi lizard, after the locality where its fossils were first discovered, is famous for its extraordinarily long neck, a feature that distinguishes it as one of the most iconic and unusual sauropod dinosaurs. Early fossils were found in the mid-20th century in Sichuan province, a geologically rich area in southwestern China. These first discoveries introduced the world to a sauropod with an exceptionally elongated neck, making up about half of the animal's total length, which could extend up to 35 meters, more than 100 feet, in some species. The towering grace of Mamenchisaurus's neck represents an intriguing evolutionary solution. Unlike many other sauropods, which evolved long necks for high browsing or niche feeding, Mamenchisaurus exhibits unique vertebral structures that allowed an unprecedented elongation without sacrificing flexibility or strength. This remarkable adaptation offers important clues about the diverse ecological roles and evolutionary pathways of sauropods in the Jurassic, showcasing the richness of dinosaur diversification beyond what early Western finds had suggested. Chinese dinosaur digs, which began earnestly in the latter half of the 20th century, have been crucial in broadening scientific horizons. Despite difficult political and economic circumstances over various decades, Chinese paleontologists persevered, conducting fieldwork and systematic excavations that unearthed not only Mamenchisaurus, but also a wide array of other sauropods, theropods, and even feathered dinosaurs that paint a vivid picture of prehistoric ecosystems. What sets the Chinese dinosaur discoveries apart is the exceptional quality of fossil preservation. The fine sedimentary matrices found in formations such as the Shaximiao and the Zia-Shaximiao formations have yielded nearly complete skeletons, often articulated, allowing detailed anatomical and biomechanical studies. The Mamenchisaurus fossils reveal articulation in the vertebrae and limb bones that help scientists reconstruct the locomotion and feeding strategies of these massive creatures with better accuracy. Furthermore, ongoing digs have uncovered multiple Mamenchisaurus species, showcasing variation in size, neck length, and body proportions. Some species display an even greater neck lengthening than previously thought, emphasizing the evolutionary experimentation within sauropods. This has broadened our understanding of how sauropods achieved gigantism and the anatomical innovations they evolved to support enormous bodies. Beyond the science itself, Chinese dinosaur research has had a profound cultural impact. Dinosaur fossils have become national treasures, fueling public enthusiasm and inspiring museums, exhibitions, and education programs throughout the country. Sites rich in fossils have often been preserved or developed into parks, making paleontology a bridge between science and cultural heritage. The endurance of Chinese dinosaur digs underlines the spirit of international collaboration that now characterizes modern paleontology. Researchers worldwide collaborate with Chinese institutions, share methodologies, and debate findings, pushing forward the boundaries of knowledge and nurturing a spirit of shared scientific progress. Mamenchisaurus and the other sauropods uncovered through these efforts illuminate the vast diversity of sauropodomorph dinosaurs and contribute to a more complete picture of dinosaurian life in the Jurassic and Cretaceous periods. Their impressive necks remain emblematic of evolutionary innovation, holding lessons about biology, ecology, and the ancient environments that supported some of the largest animals ever to walk the Earth. As we continue this voyage through dinosaur discoveries, we will next explore another giant, the elusive and enigmatic Spinosaurus, discovered and rediscovered amidst the shifting sands and rivers of northern Africa. Yet before turning to that aquatic giant, the enduring story of Mamenchisaurus invites us to appreciate how perseverance in exploration and a global scientific community continually brings new wonders to light, deepening our understanding of prehistoric life while connecting us to the mysteries of a distant age. Spinosaurus holds a unique and enigmatic place in the world of dinosaur paleontology, not only as one of the largest and most distinctive predatory dinosaurs ever discovered, but also because of its complex history of discovery, loss, and remarkable rediscovery. Often dubbed the river monster due to its presumed semi-aquatic lifestyle, Spinosaurus has reshaped scientific perceptions of dinosaur ecology and adaptation. The story of Spinosaurus began in the early 20th century during European expeditions to North Africa. In 1912, German paleontologist Ernst Stromer led fieldwork in Egypt's Bahariya oasis, unearthing fossils that would astonish the scientific community. Among these were the partial remains of a gigantic theropod dinosaur distinguished by its enormous neural spines, elongated, blade-like bones projecting from the vertebrae, that later inspired the species name Spinosaurus aegyptiacus, literally, Egyptian spine lizard. These high spines formed a distinctive sail or hump atop its back, perhaps involved in display, thermoregulation, or species recognition. Spinosaurus was remarkable not only for its size, rivaling or even surpassing the famed Tyrannosaurus rex, but also because its anatomy suggested a lifestyle unlike typical terrestrial carnivores. Fragmentary evidence indicated a crocodile-like snout and conical teeth suited for catching fish, hinting at a semi-aquatic predator adapted to life in rivers and wetlands. Tragically, much of Stromer's original fossils were destroyed during World War II in a bombing raid on Munich, leaving only descriptions, drawings, and photographs to preserve knowledge of Spinosaurus. For decades, it remained one of the most mysterious dinosaurs, with limited material fueling debate and speculation about its true nature. The story took a dramatic turn in the 21st century. Starting in the 1990s and accelerating into the 2000s, renewed fossil hunting in Morocco's Kem beds uncovered abundant remains attributed to Spinosaurus, revitalizing scientific understanding. Remarkably, multiple partial skeletons were found, including more complete fossils than ever before. These discoveries culminated in a landmark 2014 study presenting the first detailed skeletal reconstruction of Spinosaurus as a quadrupedal, semi-aquatic dinosaur. The first recognized dinosaur adapted to an aquatic lifestyle with paddle-like feet and a deeply keeled tail suited for swimming. This revelation challenged conventional images of dinosaurs as exclusively land dwellers and expanded our understanding of their ecological diversity. Spinosaurus appeared to have occupied a niche similar to that of modern crocodilians or giant aquatic predators, hunting fish and possibly venturing into open water, an extraordinary adaptation among theropods. The rediscovered Spinosaurus also reshaped the global narrative of African dinosaur paleontology, highlighting the unique faunas that thrived in Cretaceous ecosystems shaped by rivers and deltas. These sediments have continued to yield important fossils, underscoring the importance of North Africa as a key region for understanding dinosaur evolution. Beyond scientific impact, Spinosaurus has captured popular imagination through museum exhibits, documentaries, and films, where its distinctive sail and aquatic habits make it an instantly recognizable and fascinating dinosaur. Its story inspires wonder not only at the diversity of prehistoric life, but also at the evolution of knowledge itself, how fossils can be lost and found, interpretations revised, and mysteries unveiled anew. The tale of Spinosaurus, the lost river monster that vanished in war and re-emerged in desert sands, exemplifies the dramas of fossil discovery, persistence, serendipity, and scientific innovation. Its journey from early 20th century discovery through near obliteration to modern renaissance stands as a testament to humanity's enduring fascination with the past and the transformative power of paleontology. Following the epic saga of Spinosaurus, we will turn to a fascinating intersection of paleontology and popular culture in the story of Dracorex hogwartsia, the spectacular Jurassic Park Easter egg linking science with the magic of storytelling. But before that enchanting encounter, the legacy of Spinosaurus beckons us to reflect on the vast, often surprising landscapes of prehistoric adaptation, where dinosaurs not only ruled the land, but also mastered the waters in ways previously unimagined. Amidst the riveting scientific discoveries and groundbreaking research chronicled throughout the history of paleontology, There are moments when popular culture and science intertwine in ways that captivate the imagination far beyond the laboratory and excavation site. One such enchanting crossover is the story of Dracorex hogwartsia, a dinosaur named with a nod to one of the most beloved cultural phenomena of the 21st century, J.K. Rowling's Harry Potter series. This spectacular Jurassic Park Easter egg beautifully encapsulates the interplay between scientific discovery and pop culture, illustrating how fossils can inspire not just knowledge, but also creativity and wonder across diverse audiences. Dracorex hogwartsia emerged from the sedimentary rocks of South Dakota, discovered in the early 2000s and formally described in 2006 by paleontologists who were struck by the dinosaur's striking cranial features. This pachycephalosaurid, or thick-headed lizard, had a skull unlike most others, adorned with spikes, bumps, and a dragon-like visage that immediately caught the eye of its discoverers. The species name hogwartsia was chosen as a deliberate homage to the Hogwarts School of Witchcraft and Wizardry, the magical academy central to Harry Potter's adventures, evoking images of dragons, magic, and fantastical creatures. The connection between Dracorex and the Harry Potter universe is no coincidence, but a playful nod that bridges the gap between the often technical world of paleontology and popular storytelling. Naming a dinosaur after a fictional school demonstrates paleontologists' recognition of the impact cultural narratives have on public engagement with science. It also reflects how dinosaurs continue to mesmerize children and adults alike, fueling wonder and curiosity that transcend purely academic pursuits. Dracorex was characterized by a flat, spiky skull rather than the dome-shaped skull typical of many pachycephalosaurs. Its exaggerated horns and ridge-like cranial ornamentation suggested it may have used its head structures in social interactions such as display or combat, although its exact behavior remains a topic of ongoing research. Moreover, some studies proposed that Dracorex might represent a juvenile stage of Pachycephalosaurus rather than a separate genus, illustrating the complexities inherent in interpreting fossil remains and the nuances of dinosaur growth and development. The popular recognition of Dracorex was greatly amplified by its association with Jurassic Park, a franchise that has captured global audiences with its captivating blend of real science and imaginative storytelling since the early 1990s. Jurassic Park's iconic dinosaur depictions sparked renewed interest in paleontology, inspiring generations to visit museums, read about dinosaurs, and even pursue careers in the field. Dracorex hogwartsia's evocative name and design made it a standout within dinosaur-themed exhibits, media, and merchandise. It exemplified how newly discovered dinosaurs continue to fuel the cultural imagination, bridging the ancient past with contemporary stories and fantasies. The dragon moniker invited comparisons to mythic creatures, reinforcing the link between paleontology and the human penchant for stories about fantastical beasts. This case also highlights a broader trend in paleontology to engage public interest by connecting discoveries with cultural references. Scientists often name new species in ways that honor famous figures, institutions, or fictional characters, creating a more accessible and memorable dialogue between science and society. Beyond entertainment, these intersections serve educational purposes, drawing attention to the value of fossils, the process of scientific discovery, and evolutionary history. They provide entry points for discussions about anatomy, ecology, and the changing Earth, making paleontology relatable and exciting. As the story of Dracorex hogwartsia reminds us, the thrill of discovery is not confined to dusty academic texts or museum relics alone. It lives vibrantly in the shared human experience of storytelling, imagination, and the desire to connect with worlds, past and imagined, that spark wonder. Moving forward, our exploration will return to more naturalistic, frozen moments of prehistoric life with the Fighting Dinosaurs, Velociraptor and Protoceratops locked in combat, a fossil assemblage that embodies drama, behavior, and the rawness of ancient ecosystems. But before diving back into these primeval battles, the tale of Dracorex stands as a joyful reminder of how science and popular culture enrich one another, inviting us all to dream alongside discovery. The early 20th century expeditions into the Gobi Desert unveiled many astonishing dinosaur fossils, but among the most extraordinary and evocative discoveries was a remarkable fossilized scene often referred to as the Fighting Dinosaurs. This gripping fossil captures a moment frozen in deep time. Two dinosaurs, Velociraptor and Protoceratops, locked in what appears to have been a fatal battle, preserving an eternal snapshot of predator and prey struggle from about 75 million years ago during the late Cretaceous period. Uncovered in the 1970s by a Polish-Mongolian paleontological expedition near Tugrikan-Shire in Mongolia's Nemecht Basin, the fossil consists of intertwined skeletons of a small, nimble theropod dinosaur, Velociraptor mongoliensis, and a robust, horned herbivore, Protoceratops andrewsi. Both animals are fossilized in a dynamic pose. The Velociraptor's sickle-shaped claw is embedded in the neck of the Protoceratops, while the smaller dinosaur's skull is caught beneath the heavy jaws and sharp beak of its opponent. This rare specimen is not just an assemblage of bones, but a direct behavioral record, offering a vivid glimpse into the interaction between these two species. Such a find is especially extraordinary because evidence of direct combat and behavior in the fossil record is exceedingly rare. Fossils usually preserve remains after the fact, without such dramatic context. Velociraptor, thanks in part to this and other specimens, is understood as an intelligent, fast predator with sharp senses and lethal claws, adaptations for hunting smaller or similarly sized prey. Protoceratops, a stocky ceratopsian herbivore roughly the size of a modern sheep, was likely a cautious forager with formidable defenses, including a powerful beak and a solid frill around its neck. Several theories explain how these two might have met their demise entangled in this way. One suggests that while Velociraptor attacked Protoceratops, a sudden landslide or dune collapse rapidly buried them both, preserving their struggle beneath sediment. Another proposes that the two could have been trapped in a sand dune or quicksand-like substrate, fighting to escape but ultimately succumbing together. The importance of the Fighting Dinosaurs fossil extends beyond its dramatic appearance. It provides critical insight into predator-prey dynamics in late Cretaceous ecosystems and allows paleontologists to study bite marks, claw wounds, and anatomical features directly associated with combat. Analysis of the fossilized injuries supports interpretations of the hunting strategies and defensive behaviors of these species. Moreover, the find has contributed to broader discussions regarding the behaviors of theropods, like Velociraptor, including social behavior and hunting techniques. While often depicted as group hunters in popular media, fossil evidence remains nuanced, with specimens like this indicating at least some instances of solitary ambush hunting. The Fighting Dinosaurs have since become emblematic of the dynamic life and death struggles of the Mesozoic world, captivating scientists and the public alike. Their fossilized battle offers a potent, tangible connection to an ancient past where life and death were perpetually intertwined in cycles of survival. Display of this fossil in museums, primarily in Mongolia and Poland, has helped educate and inspire generations about the complexity of prehistoric ecosystems and the evidence paleontology can yield about behavior, not just anatomy. This intimate fossilized duel not only enriches our understanding of Velociraptor and Protoceratops, but also illustrates the power of fossil discoveries to transcend time, narrating stories of ancient life in vivid, relatable terms. Looking onward from this dramatic combat, we prepare to explore the immense discovery of Dreadnoughtus, a colossal titanosaur whose tremendous size challenges previous conceptions of dinosaur gigantism. But before that journey to unprecedented scale, the Fighting Dinosaurs leave us with a timeless image of struggle, adaptation, and the raw realities of prehistoric ecosystems. As we leave behind the vivid struggle embodied by the Fighting Dinosaurs, we move into an entirely different domain of the prehistoric world, a realm dominated by giants of such staggering size that their very existence challenges our understanding of biology, ecology, and the limits of terrestrial life. Central to this narrative is Dreadnoughtus shrani, a colossal titanosaur whose recent excavation has reshaped the scientific conversation about dinosaur gigantism and the scale of life during the late Cretaceous period. Discovered in 2005 in southern Patagonia, Argentina, a region famed for yielding some of the heaviest and largest dinosaurs ever known, Dreadnoughtus quickly became a star among sauropods, not only because of its size, but because of the extraordinary completeness of the skeleton unearthed. Unlike many gargantuan dinosaurs, whose fossils are often fragmentary, the remains of Dreadnoughtus provide scientists with one of the most comprehensive looks at the anatomy of a truly massive titanosaur. The name Dreadnoughtus, derived from the early 20th century British battleships known for their unprecedented size and power, aptly conveys the formidable scale and might of this dinosaur. Preliminary estimates suggest that Dreadnoughtus weighed around 59 metric tons, equivalent to about 7 to 8 modern African elephants, or roughly 65 tons by some calculations, making it among the heaviest land animals known to science. It measured approximately 26 meters, about 85 feet, in length, with a long neck and tail balanced by a massive muscular body. Beyond raw size, the significance of Dreadnoughtus lies in its remarkably well-preserved fossil material, including shoulder blades, vertebrae, limbs, pelvis, and portions of the skull, allowing researchers to conduct detailed biomechanical and growth analyses. The skeleton's articulation and the insight into its bone microstructure have opened new doors in understanding how titanosaurs supported their immense weight and moved their colossal frames. Scientists have been able to model muscle attachments, growth rates, and even infer aspects of its metabolism. One of the key revelations from Dreadnoughtus is how this massive herbivore achieved its size in relatively rapid growth bursts, similar to some modern mammals but unlike reptiles, hinting at diverse growth strategies among dinosaurs. Such studies compel paleobiologists to rethink the energetic demands, feeding behaviors, and life histories of gigantic sauropods. Dreadnoughtus has also ignited renewed discussions about the ecosystem dynamics of Cretaceous Patagonia. Living alongside many other giant dinosaurs, including equally titanic herbivores and large theropods, Dreadnoughtus inhabited floodplains rich in vegetation, where its enormous size likely deterred predators and facilitated access to high foliage. The excavation itself was a colossal undertaking. Remote dig sites, challenging weather, and rugged terrain formed a backdrop to painstakingly extracting massive bones encased in sandstone. The process required months of careful excavation, wrapping, and shipping before detailed laboratory study could begin. The commitment exemplified in this expedition reflects the dedication of modern paleontologists in unraveling the mysteries of Earth's deep past. Furthermore, Dreadnoughtus represents an important chapter in the ongoing exploration of South America's dinosaur heritage, a region that continues to yield some of the most spectacular and scientifically valuable fossils. Its discovery underscores Patagonia's status as a global center for understanding dinosaur evolution, diversity, and gigantism. In a broader context, Unraveling the biology of Dreadnoughtus informs not just dinosaur paleontology, but also the limits of terrestrial vertebrate size, biomechanics, and evolutionary adaptation. Each bone contributes pieces to the puzzle of how life can evolve to such grand proportions and what ecological factors support the sustainability of such giants. The colossal titan that is Dreadnoughtus opens the door to reassessing how we perceive dinosaurs, not just as prehistoric curiosities, but as complex, thriving organisms with sophisticated life strategies shaped by millions of years of evolutionary pressures. Our exploration will next steer toward earlier epochs and environments, where smaller but no less fascinating assemblages like the Ghost Ranch Coelophysis shed light on mass death events and the intricate stories fossil accumulations tell. Yet, before that shift, the monumental shadow of Dreadnoughtus invites us to contemplate the awe-inspiring scale and resilience of life in the Mesozoic, a world of giants ruled by titans whose bones still echo across the ages. Nestled in the vibrant red rock formations of Ghost Ranch, New Mexico, lies a paleontological treasure that has captivated scientists and enthusiasts for nearly a century: the mass death assemblages of Coelophysis. These fossils represent not just individual creatures long extinct, but a dramatic chapter in Earth's evolutionary history, providing insight into dinosaur behavior, ecology, and the conditions of the late Triassic period, approximately 210 million years ago. Coelophysis borii, a slender, agile theropod dinosaur, was among the earliest carnivorous dinosaurs. Measuring roughly 3 meters, about 10 feet long, it sported a long neck and tail, sharp, recurved teeth, and lightweight bones that made it an efficient predator. Its discovery at Ghost Ranch is significant due to the sheer quantity and remarkable preservation of fossils found there. Thousands of individuals buried together in what paleontologists call a bone bed. The discovery of the Ghost Ranch bone beds began in the 1940s when paleontologists first excavated the site, revealing an unprecedented accumulation of Coelophysis skeletons. Over time, the site has yielded hundreds of individual specimens, many remarkably complete and articulated. The extent and sudden burial of these animals suggest a catastrophic event, such as a flash flood or rapid sedimentation, that overwhelmed a population gathered in proximity. Such mass death assemblages are critical to understanding not only the anatomy of Coelophysis, but also the social dynamics these early dinosaurs might have exhibited. The close proximity of individuals raises questions about their behavior. Did these dinosaurs travel in packs or loosely associated groups? While direct evidence of complex social behavior remains elusive, the fossil record at Ghost Ranch allows scientists to explore these hypotheses by examining bone orientation, age distribution, and growth patterns. The assemblage also provides invaluable data on population structures. Detailed studies have revealed a mix of juvenile and adult specimens, indicating that these dinosaurs lived in groups that included multiple age classes, which would have implications for survival strategies and predator-prey dynamics in their ecosystems. Beyond behavior, the Ghost Ranch Coelophysis fossils serve as a window into the environmental conditions of late Triassic North America. The rapid burial of these dinosaurs in a sedimentary context rich with river deposits and floodplain sediments illustrates a world in flux, where changing climates and geology influenced the rise and fall of early dinosaurs. Remarkably, some specimens from Ghost Ranch also show evidence of injuries and pathologies, such as healed bone fractures and bite marks, telling a further story of the challenges these animals faced during their lifetimes, from intraspecific combat to predator-prey encounters. These pathological insights humanize them, turning distant fossils into stories of survival, struggle, and life. The Ghost Ranch discoveries have also been pivotal in understanding dinosaur evolution. Coelophysis is often considered a basal, or primitive, theropod, making it essential for piecing together the early diversification of dinosaurs that eventually led to the emergence of giants like Tyrannosaurus and Velociraptor, as well as the lineage that culminated in modern birds. The site continues to be a focal point for paleontological research. Advances in technology, such as CT scanning and isotopic analysis, enable deeper investigations into growth rates, physiology, and paleoecology. Combined with traditional fieldwork, these methods enrich our comprehension of Coelophysis and the world it inhabited. As one stands amidst the Ghost Ranch landscape today, the heat-etched cliffs and sprawling mesas echo the silent impressions of an ancient tragedy and a remarkable survival tale written in bone. This mass death assemblage not only illuminates a specific moment frozen in time, but also embodies the broader journey of paleontology, how layers of Earth preserve stories waiting patiently to be heard. From the late Triassic plains of Ghost Ranch, our voyage of discovery turns south to the wild and competitive arenas of Cretaceous South America, where titanic predators like Giganotosaurus and Carcharodontosaurus stood toe-to-toe with Tyrannosaurus rex. But before we venture there, the Ghost Ranch Coelophysis specimens remind us of the interconnectedness of the fossil record, weaving a continuous thread across epochs, environments, and evolutionary milestones. In the grand tapestry of dinosaur discovery, few tales captivate the imagination quite like those of the colossal theropods that once roamed South America: Giganotosaurus and Carcharodontosaurus. These giant predators not only rival the famed Tyrannosaurus rex in size and ferocity, but also represent a distinct evolutionary lineage that enriches our understanding of dinosaur diversity and the dynamics of predation in the late Cretaceous. Their fossils tell a story of powerful hunters that challenged the preeminence of T-Rex in the popular imagination and unveiled complex ecosystems thriving millions of years ago. Giganotosaurus carolini was first discovered in the 1990s in Patagonia, Argentina, among sedimentary rocks dating to approximately 98 million years ago during the Cenomanian stage of the late Cretaceous. The discovery was a landmark moment, with a skull length exceeding 1.5 meters, about 5 feet, and an estimated length of up to 13 meters, over 43 feet. Giganotosaurus was one of the largest known terrestrial carnivores. Its robust build, powerful jaws, and serrated teeth indicated a formidable predator adapted to hunting massive sauropods like Argentinosaurus, some of the largest animals ever to walk the earth. Shortly after, Carcharodontosaurus saharicus was unearthed in the Kem beds of Morocco, dating roughly 100 to 93 million years ago. Named for its shark-like teeth, Carcharodontosaurus means shark-toothed lizard. This giant theropod also rivaled T-Rex in size and likely occupied a similar apex predator role in its ecosystem. Carcharodontosaurus possessed a long skull filled with blade-like teeth optimized for slicing flesh, and its skeletal morphology suggested adaptability for swift, powerful strikes. These two giants underscore the global distribution and diversity of Carcharodontosaurids, a group distinct from the tyrannosaurs native to North America and Asia. Their evolution unfolded in the vast southern continents of Gondwana, providing clues about continental drift and paleobiogeography. Additionally, their presence alongside enormous herbivorous dinosaurs suggests complex predator-prey relationships and niche partitioning in prehistoric ecosystems. The rivalry between their fossils and the celebrated T-Rex sparked spirited debate among paleontologists and the public alike. Although T-Rex retains iconic status, Giganotosaurus and Carcharodontosaurus rival its size and provide compelling alternative narratives about predatory dominance in different regions and periods. This comparison highlights that the Mesozoic era was home to multiple apex predators, each adapted to unique environments and prey. From a scientific perspective, studying their skeletal remains has offered insights into theropod anatomy, growth patterns, and biomechanics. For example, analyses of limb proportions and muscle attachments informed estimates of running speed and hunting strategies, while cranial studies elucidated bite force and feeding mechanics. These findings enrich our vision of how such massive predators lived, hunted, and interacted with other members of their ecosystems. Moreover, the South American and North African finds demonstrate how new discoveries continually reshape dinosaur paleontology, exposing previously hidden chapters of prehistoric life and revising assumptions based on earlier, more limited data. The abundance and quality of these skeletons enable reconstructions that are increasingly accurate and dynamic. Beyond science, Giganotosaurus and Carcharodontosaurus have permeated popular culture, featuring in documentaries, exhibitions, and media, often portrayed as fierce and awe-inspiring adversaries that complement or challenge the T-Rex narrative. Their stories invite us to appreciate the profound diversity and wonder of the dinosaur world, extending far beyond the familiar to realms once obscured by time and distance. As we continue our exploration, we'll next encounter the armored marvels of the late Cretaceous, beginning with Ankylosaurus and its remarkable journey from fragmentary remains to iconic reconstructions. These armored giants provide yet another dimension to the prehistoric panorama, a testament to evolutionary innovation that balanced offense and defense in the age of dinosaurs. But the saga of Giganotosaurus and Carcharodontosaurus remains a powerful testament to the scale, power, and ecological complexity of prehistoric predators, whose bones echo with stories of ancient dominance and survival in the distant past. In the sprawling canvas of dinosaur history, some of the most fascinating creatures are those that carried their defense directly upon their bodies, the armored dinosaurs. Among these, Ankylosaurus stands out as a symbol of nature's ingenuity, embodying a remarkable marriage of offense and defense that has captivated scientists and the public alike. The journey to understand Ankylosaurus, from fragmentary remains to fully formed, iconic museum reconstructions, tells a rich story of persistence, interpretation, and technological innovation in paleontology. Ankylosaurus, roughly translating to fused lizard, is famed for its heavily armored body, studded with bony plates, and its distinctive club-like tail, used as a formidable weapon against predators. First described scientifically in the early 20th century based on limited fossil fragments found in the western United States and Canada, these remains initially offered tantalizing yet incomplete glimpses of a dinosaur designed for defense. Early fossil finds included isolated osteoderms, bony plates embedded in the skin, fragments of vertebrae, limb bones, and bits of skull material. This scatter of pieces posed a challenge for paleontologists who sought to reconstruct the full anatomy and lifestyle of Ankylosaurus. The gaps in the fossil record meant early artistic renderings and museum displays had to rely heavily on educated guesses, comparisons with related species, and imaginative reinterpretations. As more complete specimens were discovered over subsequent decades, including articulated skeletons with well-preserved armor, paleontologists began piecing together a clearer picture. The heavy shield of osteoderms formed a complex armor scheme, protecting the dinosaur from head to tail, with large clubs at the end of the tail capable of delivering powerful blows. This defensive adaptation likely evolved in response to contemporaneous large carnivores like Tyrannosaurus rex. From the fragmentary remains surfaced an image of a low-slung, stout-bodied dinosaur, built more for resilience than speed, but equipped to deter or incapacitate attackers. The structure of its legs and feet supports a slow but steady gait, while its broad body provided ample space for gut fermentation needed to digest tough vegetation. Technological advances in paleontology greatly enhanced our understanding of Ankylosaurus. Detailed CT scans of skulls have revealed sensory capabilities and brain structures, showing this dinosaur possessed acute senses, potentially aiding in detecting predators or foraging cues. Microscopic analysis of armor and bone confirms sophisticated growth patterns and sheds light on its biology and physiology. Museum mounts of Ankylosaurus evolved from early static dioramas to dynamic life-sized reconstructions, often preserved with accurate scales and anatomically faithful postures. These exhibitions have solidified the dinosaur's iconic status, bringing to life a creature that seems almost otherworldly in its defensive grandeur. Beyond Ankylosaurus itself, the discovery and reconstruction of armored dinosaurs more broadly open windows onto the diversity of Mesozoic defensive strategies. From nodosaurids with spiked armor to the unique tail clubs of ankylosaurids, these armored marvels present a compelling evolutionary narrative, one where evolutionary arms races spurred complex adaptations. Their fossils often preserve not only bones, but impressions of skin texture, offering glimpses of the rough, scaly surfaces of their armor. Such exquisite preservation helps paleontologists connect anatomy with function and ecology. The story of Ankylosaurus is also a testament to the scientific method, showing how fragmentary evidence can be transformed into comprehensive understanding through careful research, comparative anatomy, and advances in imaging and display techniques. As we prepare to explore the exceptional preservation of Borealopelta, often described as a dinosaur mummy, Ankylosaurus's journey reminds us of the power of fossils to bridge millions of years, bringing the armored marvels of prehistory into sharp, tangible focus for modern audiences. Among the most extraordinary fossil discoveries in recent paleontological history is the remarkable specimen of Borealopelta markmichelli, unearthed in Alberta, Canada, and known for being one of the best preserved dinosaur. Our journey into the Mesozoic era's rich tapestry of life takes an intimate turn as we delve into the fascinating world of oviraptor nests, remarkable fossilized sites that have redefined long-standing perceptions about dinosaur behavior, particularly parental care, and offered rare glimpses into the daily lives of Cretaceous theropods. These discoveries have played a pivotal role in transforming our understanding from seeing dinosaurs merely as cold-blooded reptiles to appreciating them as dynamic creatures with complex social behaviors akin to modern birds. Oviraptor, meaning egg thief, originally earned its curious name from a discovery in the 1920s. Paleontologists uncovered a fossilized skeleton of this small to medium-sized feathered theropod near a nest of eggs. Their initial interpretation was that the dinosaur had died while attempting to steal and eat another species' eggs. This portrayal of Oviraptor as a reckless egg thief would, however, be radically revised by later and more comprehensive fossil evidence. Subsequent excavations, particularly in the rich late Cretaceous deposits of Mongolia's Gobi Desert, revealed numerous oviraptor nests where fossilized skeletons were found positioned atop or nestled within clutches of their own eggs. These discoveries highlighted the possibility that oviraptors were brooding their eggs much like modern birds, protecting and incubating them rather than attempting to pilfer them. This compelling evidence overturned over half a century of assumptions and reframed Oviraptor as a caring parent, the antithesis of its initial reputation. The nests themselves are extraordinary. They typically contain numerous oval-shaped eggs arranged in tight circles, sometimes in multiple layers, suggesting highly organized and possibly communal nesting behaviors. The adult skeletons were found in postures strikingly reminiscent of brooding birds, with limbs spread protectively over the eggs, further reinforcing the concept of active parental care. Studies of eggshell microstructures and embryonic remains inside some of these eggs have shed light on the development rates, incubation conditions, and reproductive biology of Oviraptor. For instance, the presence of developing embryos within eggs confirms the identification of the nests, while eggshell characteristics hint at the environmental conditions and whether eggs were incubated with body heat or solely by external factors. Complementing these findings are insights into the anatomy and possible behavior of Oviraptor itself. As a member of the theropod lineage closely related to modern birds, Oviraptor possessed feathers, agile limbs, and a beak-like mouth, indicative of an active lifestyle that likely included brooding and nest attendance. These traits intertwine anatomy with behavior, portraying a creature far from the primitive reptile archetype. The re-evaluation of Oviraptor's role in nesting has broader implications as well. It suggests that avian-style parental care, incubation, protection, possibly even nurturing behaviors, originated deep within theropod dinosaurs, predating the evolution of birds themselves. Such behavioral continuity marvelously connects extinct non-avian dinosaurs with their living descendants, offering a richer evolutionary narrative. Moreover, the discovery of Oviraptor nests contributes to understanding dinosaur reproductive strategies, including clutch size, nesting frequency, and hatchling development, factors that influence survival and population dynamics. These clues help reconstruct the delicate balance of Cretaceous ecosystems where dinosaurs thrived. Oviraptor's story also challenges simplistic stereotypes about dinosaur diets and behaviors. While originally labeled an egg thief, current evidence indicates a more omnivorous or specialized diet, possibly including plants, small animals, and eggs, complemented by complex social behaviors. This nuanced image enriches our appreciation of theropod diversity and adaptability. In museums and scientific literature, the depiction of Oviraptor brooding nests continues to inspire public fascination, bridging science and storytelling. It humanizes dinosaurs, allowing audiences to connect emotionally with behaviors of care, protection, and life cycles, fostering a deeper interest and empathy. In summary, the unveiling of Oviraptor nests has been a watershed moment in paleontology, rewriting textbooks and reimagining dinosaur lives as creatures capable of care and social complexity. This discovery strengthens the evolutionary link to birds and demonstrates the vitality of interdisciplinary approaches, combining fossil anatomy, nesting behavior, embryology, and ecology to unravel the rich stories held in stone. As we proceed, we will explore the remarkable case of Sinosauropteryx and the explosion of feathered dinosaurs from Liaoning, China, where further fossil finds continue to illuminate the ancestral roots of avian feathers and the diversity of plumage in prehistoric times. But before we take flight with these feathered forebears, the tale of Oviraptor nests stands as a testament to how paleontology continues to reveal the intimate behaviors that shaped dinosaur evolution and the ecosystems they inhabited. In the early days of dinosaur paleontology, the idea of dinosaurs sporting feathers was largely dismissed or unknown. However, groundbreaking discoveries from the Liaoning province in northeastern China during the 1990s and early 2000s transformed this notion entirely. Among these discoveries, Sinosauropteryx holds a special place as one of the first non-avian dinosaurs conclusively shown to have feathers, igniting a scientific revolution and an explosion of research into feathered dinosaurs. Sinosauropteryx prima, described in 1996, was a small theropod dinosaur roughly the size of a modern turkey. It lived approximately 125 million years ago during the early Cretaceous period. Its fossils were uncovered in the well-preserved sedimentary rock formations of the Yixian Formation, part of the famed Liaoning fossil beds, which have yielded an unprecedented diversity of feathered dinosaur specimens. What made Sinosauropteryx extraordinary was the exquisite preservation of filamentous structures covering its body. These simple, hair-like filaments represented the most primitive known feathers, often referred to as proto-feathers, marking the earliest evolutionary stages of feather development. This discovery was monumental because it provided concrete evidence that feathers were not exclusive to modern birds, but were present in a wider array of theropod dinosaurs, including their close dinosaurian relatives. The preserved feathers of Sinosauropteryx were not just a scientific curiosity. They allowed researchers to investigate coloration and camouflage strategies. Through meticulous analysis of fossilized pigment cells known as melanosomes, scientists inferred that Sinosauropteryx exhibited a distinctive countershading pattern, darker on its back and lighter underneath, a common mechanism among modern animals to evade predators and prey by reducing visual contrast. This suggested that early feathers had functional roles beyond flight, such as insulation and display. The discovery of feathered dinosaurs in Liaoning sparked a surge of fossil finds, revealing a diversity of feather types and complexities in various theropods, from simple filaments to complex, branching feathers. These new fossils challenged long-standing views of dinosaur anatomy and biology and provided compelling evidence for the evolutionary lineage of birds. Sinosauropteryx and its Liaoning contemporaries have also been essential in deepening our understanding of dinosaur ecology and behavior. The fossil beds often preserve not only feathers, but also stomach contents, eggs, and even footprints, painting detailed pictures of interactions within prehistoric ecosystems. The Liaoning fossils also highlight the exceptional preservation conditions of the area, where fine volcanic ash quickly buried organisms, enabling extraordinary detail in skeletal and soft tissue preservation. This Lagerstätte, a site of exceptional fossil preservation, remains one of the richest sources of information about feathered dinosaurs worldwide. Beyond science, the revelations about Sinosauropteryx and feathery dinosaurs have had broad cultural impact, shaping museum exhibitions, documentaries, and even Hollywood's depiction of dinosaurs, making these ancient creatures appear more dynamic and bird-like than ever before. As we prepare to journey to the vast landscapes of Patagonia and meet the lost giants like Argentinosaurus, the story of Sinosauropteryx underscores the continuous thread of discovery, how each fossil find not only fills gaps in knowledge, but also often overturns long-held assumptions, enriching our vision of the vibrant, evolving world of dinosaurs. In the vast and wind-swept landscapes of Patagonia, nestled in the southern reaches of South America, paleontologists have uncovered some of the largest land animals known to science, the titanic sauropods that reigned as true giants of the Cretaceous period. Among these colossal creatures, Argentinosaurus stands as a monumental icon, often hailed as the king-sized giant, whose sheer magnitude challenges and fascinates us even today. Argentinosaurus huinculensis was first discovered in the 1980s near Plaza Huincul in Argentina, a region that has become a treasure trove for massive dinosaur fossils. Unlike many earlier sauropods known from more fragmentary remains, Argentinosaurus is estimated based on extrapolation from substantial vertebrae and limb bones to have reached lengths exceeding 30 meters, around 98 feet, and weights upwards of 70 to 100 metric tons, making it among the largest, if not the largest, land animals ever to roam the Earth. What makes Argentinosaurus and its Patagonian contemporaries so extraordinary is not merely their size, but what they reveal about the limits of gigantism in terrestrial vertebrates. Their enormous bodies required remarkable adaptations: robust limb bones to support immense weight, complex respiratory and circulatory systems to maintain vital functions, and skeletal structures optimized for both strength and relative lightness through hollow bones. Fossils from Patagonia, including Argentinosaurus, facilitate valuable insights into sauropod anatomy and evolution. The immense vertebrae contain pneumatic cavities, air-filled spaces similar to those in modern birds, reducing weight without compromising strength. This feature, along with the dinosaur's long, flexible neck, enabled these giants to graze vast areas while remaining mostly stationary, efficiently exploiting the lush Cretaceous vegetation. Patagonia's fossil beds have yielded not just Argentinosaurus, but a rich diversity of other giant sauropods like Protoceratops and Elongated-necked, each contributing to a broader picture of sauropod diversity and ecological dynamics. These monsters roamed floodplains and forested regions that, despite their size, supported an astonishing array of life, including equally massive herbivores and their predators. Excavating these giants is a monumental task. The sheer scale of the bones demands specialized equipment and expertise. Many fossils remain partially uncovered due to the vastness of their size, and some are known only from isolated elements, requiring paleontologists to piece together clues from multiple specimens to reconstruct the whole animal. The discovery of Argentinosaurus sparked a re-examination of prehistoric ecosystems and the energetic demands of sustaining such titans. Scientists ponder how much food would be necessary to fuel a massive sauropod and what climate and plant life could support them. These considerations deepen our understanding of Mesozoic environments and the complex interactions between species. Argentinosaurus and the lost giants of Patagonia are more than just objects of fascination. They are a testament to life's extraordinary capacity for growth and adaptation. Standing as living monuments of evolution's grandeur, these dinosaurs stretch our imagination and scientific inquiry into the realm of the colossal. Their fossils inspire awe and fuel research, perpetually reshaping our appreciation for the prehistoric world. As we move forward, our story takes us to the Utahraptor megablock, where a deadly cluster of giant dromaeosaurs intertwines tales of predation, fossil preservation, and scientific unraveling. A thrilling continuation of the saga of dinosaur discovery and interpretation. In the rugged terrains of what is now eastern Utah, a remarkable fossil discovery has brought to light a violent episode frozen in time, involving a cluster of giant predatory dinosaurs known as Utahraptors. This extraordinary find, commonly referred to as the Utahraptor megablock, represents one of the most complex and tantalizing paleontological puzzles. A mass assemblage of large dromaeosaurs that offers unprecedented insights into the behavior, ecology, and social structures of these formidable theropods during the early Cretaceous period, approximately 125 million years ago. Utahraptor ostrammesorum, the dinosaur at the center of this discovery, is widely regarded as the largest known member of the dromaeosaur family, the group to which the famed Velociraptor also belongs. Measuring up to 7 meters, nearly 23 feet in length, and equipped with a curved, sickle-shaped claw on each foot, Utahraptor was a formidable predator, likely occupying the apex of its ecosystem. The megablock site comprised multiple individuals, both adults and juveniles, entangled within a single geological deposit, suggesting that these dinosaurs may have been engaged in a fierce confrontation, social interaction, or fallen victim to a disastrous event that preserved them together. The fossil assemblage is especially significant for its scale and preservation. Unlike solitary skeletons or isolated bones that are typical in the fossil record, the Utahraptor megablock comprises a dense cluster of skeletons, some partially articulated embedded within a sandstone matrix. The complexity of disentangling the intertwined bones, many overlapped or embedded in close proximity, has challenged paleontologists to reconstruct not only individual anatomies, but to interpret the broader scene in which these creatures met their end. Researchers have proposed multiple hypotheses regarding the nature of this mass deposit. One possibility is that it represents a social aggregation of Utahraptors, perhaps a hunting party or family group. While direct evidence of complex social behavior in large theropods remains debated, the cluster raises intriguing questions about cooperative hunting or pack behavior among the giant dromaeosaurs. Alternatively, the site might capture the aftermath of a catastrophic event, such as a flash flood or sand dune collapse, which rapidly buried a group of these dinosaurs. This preserves a snapshot of their existence abruptly halted, offering a rare window into paleoecology and environmental dynamics during the early Cretaceous. The Utahraptor megablock has enabled scientists to analyze the morphology, growth patterns, and potential sexual dimorphism within the species with greater statistical significance, given the number of individuals present. This has deepened understanding of variation within the species and developmental trajectories from juveniles to fully grown adults. Furthermore, the assemblage provides clues about predator-prey dynamics, as Utahraptors would have coexisted with various herbivorous dinosaurs, suggesting complex ecological interplays. The formidable claws of Utahraptor, combined with its agility inferred from skeletal anatomy, emphasize its role as a powerful hunter. Excavations and preparations of the megablock have required innovative paleontological techniques. Given the dense overlapping fossils, advanced imaging technologies such as CT scanning and 3D modeling have been employed to visualize the bones within the matrix, aiding in careful extraction and reconstruction without damage. The Utahraptor megablock stands as a testament to the intricacies of ancient ecosystems and the sometimes tragic events that capsules fossilized moments in time. It bridges the gap between the often isolated museum specimen and the dynamic social and environmental contexts in which these creatures lived. As we transition from this cluster of deadly hunters, our journey will next delve into the bone beds of Dinosaur Provincial Park, where vast accumulations of ceratopsians, hadrosaurs, and other dinosaurs reveal the scale and variety of late Cretaceous faunas in North America. But before moving forward, the Utahraptor megablock invites reflection on hunting strategy, social behaviors, and the powerful stories fossil assemblages can tell about prehistoric life in all its complexity and immediacy. Dinosaur Provincial Park, located in the heart of Alberta, Canada, is one of the most prolific and scientifically significant dinosaur fossil sites on the planet. This UNESCO World Heritage Site is nothing short of a paleontological treasure trove, housing sprawling bone beds that have yielded an astounding diversity of dinosaur fossils, particularly those of ceratopsians and hadrosaurs, two of the most iconic and abundant groups of late Cretaceous herbivores. The scale and richness of these bone beds provide a window into the ecosystems that thrived approximately 75 to 74 million years ago and offer profound insights into dinosaur ecology, behavior, and evolution. The story of Dinosaur Provincial Park's bone beds begins with the recognition that large masses of dinosaur bones were preserved together in sedimentary layers. These bone beds often contain thousands of bones from multiple species, sometimes disarticulated but not scattered far, suggesting mass death events, possibly caused by floods, droughts, or other environmental catastrophes. The sheer density of fossils transforms these deposits into invaluable resources for reconstructing entire communities rather than isolated species. Ceratopsians, the horned dinosaurs, are well represented in these bone beds. Species such as Centrosaurus, Styracosaurus and Chasmosaurus provide a spectrum of evolutionary adaptations in skull ornamentation, horns, and frills that likely played roles in species recognition, sexual display, and defense. Fossil finds include both adults and juveniles, allowing paleontologists to study growth patterns and social structures. The presence of large herds, suggested by the bone beds, indicates that ceratopsians might have relied on group living for protection against predators and cooperative care of young. Hadrosaurs, or duck-billed dinosaurs, are another dominant group represented abundantly in these bone beds. Species like Corythosaurus, Gripposaurus, and Lambeosaurus are notable for their elaborate cranial crests and sophisticated chewing apparatuses. The concentration of hadrosaur remains across various age groups, hints at complex social dynamics, migratory behavior, and reproductive strategies. Their fossils also reveal details about diet, such as the presence of gastroliths, stomach stones, and tooth wear patterns, illuminating how these animals processed vegetation. The Dinosaur Provincial Park bone beds have yielded more than just isolated bones. They have preserved nests, trackways, and even evidence of predation, offering holistic insight into life and death in the Cretaceous. The co-occurrence of predator and prey fossils nearby paints visceral pictures of ecological interactions, including the presence of formidable theropods like Albertosaurus. Importantly, the park's bone beds have propelled scientific understanding forward, allowing for comprehensive paleoecological reconstructions. By examining bone bed composition, sedimentology, and taphonomy, the processes of decay and fossilization, researchers can infer ancient climate patterns, seasonal behaviors, and environmental stresses that shaped dinosaur populations. The continuous discoveries at Dinosaur Provincial Park have made it a vital training ground for paleontologists worldwide, blending meticulous fieldwork with state-of-the-art laboratory analyses. Cutting-edge techniques such as CT scanning, isotopic analysis, and ancient DNA research, where applicable, augment traditional paleontological approaches, enhancing our grasp of dinosaur biology and evolution. As a symbol of these remarkable efforts, Dinosaur Provincial Park serves not only scientists, but also the public, attracting thousands of visitors who engage with interpretive programs that bring to life the world of ceratopsians and hadrosaurs. Educational outreach underscores the importance of conservation, both of fossil sites and the modern ecosystems they inspire us to protect. Moving ahead, our exploration will shift to the remarkable realm of preserved soft tissues inside dinosaur bones, a frontier that continues to astound scientists and redefine what fossilization can reveal about ancient life. Yet, before stepping into this microscopic and molecular world, we take a moment to appreciate Dinosaur Provincial Park's bone beds, a vivid tableau of prehistoric communities and a testament to the wealth of knowledge that arises when thousands of bones whisper together across the eons. Among the most astonishing advancements in paleontology in recent decades is the discovery of preserved soft tissues within dinosaur bones, an extraordinary revelation that challenges long-held assumptions about fossilization and opens new frontiers in understanding the biology, evolution, and ecology of dinosaurs. These rare finds, fibers, blood vessel structures, proteins, and sometimes even cellular remnants, offer an unprecedented window into the ancient past, illuminating details previously thought lost to the ravages of time. For much of the history of dinosaur research, fossils were understood primarily as mineralized bones, the hard, durable parts of ancient organisms enduring over millions of years. Organic tissues, being perishable, were believed to decay completely, leaving only skeletal remnants. However, groundbreaking work beginning in the early 2000s challenged this paradigm. The breakthrough came when researchers, led by Mary Schweitzer, while studying a Tyrannosaurus rex fossil, identified microscopic structures resembling blood vessels, cells, and connective tissues still preserved within fossilized bone. The soft tissues were remarkably pliable and exhibited chemical signatures consistent with collagen, a primary protein in bone and connective tissue. This discovery was revolutionary, suggesting that under exceptional circumstances, molecular and structural components of soft tissues can survive deep geological time. Since then, similar findings have been reported from a variety of dinosaur fossils around the world, including hadrosaurs, theropods, and sauropods. These preserved materials have permitted scientists to probe the molecular makeup of long-extinct creatures, enabling comparisons with modern birds and reptiles. Such analyses refine phylogenetic relationships and provide clues about dinosaur physiology, metabolism, and health. One of the hallmarks of these discoveries is the identification of pigments such as melanin preserved in feather and skin impressions. This has allowed reconstructions not only of dinosaur shapes, but also their coloration, patterns, and potentially even camouflage or display functions. Beyond pigments, the presence of proteins and other biomolecules invites the tantalizing possibility of studying ancient immune systems, diseases, and growth processes. The preservation of soft tissues is exceedingly rare and depends on unique geological conditions, rapid burial, anoxic environments limiting decay, and mineralization processes that stabilize organic molecules. These circumstances often occur in fine-grained sediments associated with lakes, floodplains, or marine settings. Technological advancements have been pivotal in these discoveries. Cutting-edge imaging techniques such as synchrotron radiation scanning, scanning electron microscopy, and mass spectrometry permit the visualization and chemical characterization of soft tissue remnants without destroying precious fossils. These methods have transformed paleontology into an increasingly molecular science. Importantly, the findings of soft tissue preservation prompt reflection on taphonomy, the processes affecting organismal remains from death to fossilization, and illuminate how life's molecular legacy can endure for millions of years. They also invigorate discussions on the limits of DNA preservation and the potential, however remote, of retrieving ancient genetic information. The implications extend beyond academic curiosity. They enrich educational narratives and deepen public fascination by making dinosaurs more tangible and vibrant creatures instead of distant bones. Museums and documentaries increasingly incorporate these discoveries to illustrate the dynamic nature of paleontological research and the continuous rewriting of scientific understanding. As we move towards the frontiers of technology aiding paleontology, from 3D scanning to synchrotrons and beyond, the study of preserved soft tissues exemplifies how innovative methods can unlock secrets long buried, continuously transforming our vision of ancient Earth and the evolutionary story of dinosaurs. In the next chapter, we explore precisely how these cutting-edge technologies are revolutionizing the search for new dinosaur skeletons and deepening our exploration into Earth's prehistoric mysteries. The field of paleontology, once reliant on painstaking manual excavation and the physical handling of delicate fossils, has entered a remarkable new era defined by cutting-edge technology. Advances such as 3D scanning, synchrotron imaging, and computational modeling are revolutionizing the way scientists discover, analyze, and interpret dinosaur skeletons and their fossilized environments. These innovations are not only speeding up and refining research processes, but also deepening our understanding of ancient life beyond what was previously imaginable. One of the technological marvels leading this transformation is 3D scanning. Using lasers, structured light, or photogrammetry, researchers can create highly precise digital replicas of fossils without physical contact. These virtual models preserve every minute detail of a specimen's surface, allowing paleontologists to study fragile bones remotely, collaborate across continents instantly, and digitally reconstruct incomplete skeletons. For instance, fragmented fossils can be virtually pieced together, providing new insights into dinosaurs' anatomy and posture. Museums around the world employ 3D scanning not only for research, but also for creating exact replicas to display while keeping originals safely preserved. Synchrotron radiation, produced by particle accelerators, offers a powerful imaging technique that enables scientists to peer inside fossilized bones at a microscopic and even molecular level. This non-destructive method produces high-resolution 3D images of internal bone structure, revealing details about growth rings, vascular canals, and even the preserved microarchitecture of tissues. Such data illuminate aspects of dinosaur physiology, health, and evolutionary traits, allowing researchers to study bone remodeling and pathology in remarkable detail. Moreover, synchrotron technology has been pivotal in detecting molecular remnants like collagen and pigments inside bones and feather impressions, confirming that soft tissues and coloration can sometimes survive fossilization. This has opened windows into dinosaur biology, such as pigmentation patterns that indicate camouflage or display, and insights on their metabolic rates and growth dynamics. Alongside imaging, computational modeling and machine learning are playing increasingly valuable roles. Paleontologists now simulate biomechanics to test hypotheses about dinosaur movement, feeding mechanics, and behavior using digital skeletons derived from scans. These models allow virtual experiments that are impossible in real life, such as stress tests on bones during locomotion or bite force estimations, enriching our understanding of how dinosaurs lived and thrived. In the field, drone technology has begun to assist with aerial mapping of fossil sites, providing topographical data quickly and accurately over large terrains. Geographical Information Systems, GIS, then integrate these maps with geological data to help locate promising excavation areas and understand sedimentary contexts that inform fossil preservation processes. Another exciting frontier is the application of deep learning algorithms to fossil identification and sorting. By training computers to recognize specific shapes and textures, large fossil collections can be cataloged more efficiently, accelerating the pace of new discoveries by highlighting overlooked or misidentified specimens. All these technological advancements ensure that paleontology is becoming a truly interdisciplinary science, blending traditional fieldwork with physics, computer science, and molecular biology. They enhance not only discovery, but also preservation, fostering public engagement through virtual reality experiences and digital archives that bring prehistoric worlds to life. As we look ahead, the ongoing search for new dinosaur skeletons is both invigorated and refined by this technology-rich environment, promising more spectacular finds and deeper revelations. With these tools at their disposal, scientists are set to unravel more secrets of Earth's ancient past, continuing the grand narrative of dinosaur discovery into the future. Our final chapter will reflect on how the cumulative fossil discoveries featured throughout this narrative continue to transform our vision of ancient Earth and the evolutionary story of dinosaurs, underscoring the profound impact each finding has on science, culture, and humanity's understanding of life's history. The extensive catalog of fossil discoveries detailed throughout our journey reveals not only the incredible diversity and complexity of dinosaur life, but also how each find continuously reshapes our understanding of Earth's ancient past and the evolutionary story of dinosaurs. From the earliest bones identified by William Buckland to the recent high-tech scans uncovering molecular remnants, paleontology is a vibrant and evolving science, with each new discovery pulling back the curtain on a dynamic world once lost in the depths of time. These discoveries illuminate the vast tapestry of prehistoric ecosystems, showing dinosaurs not as isolated curiosities, but as integral parts of complex food webs and habitats. The revelation of marine reptiles by Mary Anning expanded our vision of prehistoric life to the oceans, while the well-preserved skeletons of Megalosaurus, Iguanodon, and Bernissart's herd opened early chapters on terrestrial giants and their social lives. Later findings, such as the famous Diplodocus carnegie, underscored not just their immense size, but their role in shaping culture and science globally. The Dueling Dinosaurs and Sue the T-Rex embody how exceptional fossil preservation provides unique behavioral insights and anatomical clarity, pushing beyond bones into life histories. Similarly, the feathered fossils from Liaoning, including Sinosauropteryx and Archaeopteryx, have revolutionized perspectives on the origin of birds and the evolution of feathers, integrating dinosaurs into the story of modern avian biodiversity. Giants like Argentinosaurus and Dreadnoughtus challenge our understanding of biological limits, while armored dinosaurs such as Ankylosaurus and Borealopelta reveal fascinating defensive strategies preserved with astonishing detail, bridging anatomy and ecology. Meanwhile, studies of soft tissues raise profound questions about molecular preservation and the biological continuity spanning millions of years. Technological advances in imaging, scanning, and computational modeling amplify our capability to investigate these fossils non-invasively and at unprecedented resolutions, ushering in an era where fine anatomical, molecular, and even behavioral data emerge from ancient bones. These tools not only accelerate discovery, but also foster international collaboration and public engagement, democratizing access to prehistoric knowledge. Collectively, these fossil discoveries underscore the ever-changing and interconnected nature of scientific knowledge. New finds challenge old assumptions, illuminate new questions, and weave ever richer narratives connecting life's distant origins to the present. They remind us that the story of dinosaurs is also the story of Earth's dynamic environments, evolutionary innovation, and the enduring human quest to understand our planet's deep history. Ultimately, the pursuit and study of dinosaur fossils continue to transform our vision of ancient Earth, revealing a world teeming with wonder, adaptation, and change, and deepen our appreciation for the evolutionary processes that have shaped life over hundreds of millions of years. This ongoing journey bridges geology, biology, and storytelling, inviting us all to explore, dream, and learn from the magnificent creatures that once ruled our world.